Okay, we're going to look at graphical analysis of uniform acceleration. So we're going to look at two graphs, position time graphs and velocity time graphs. So in the first one part here, we're going to look at position time graphs. So position time graphs, there's two things we can get from it. We can get what's known as the average velocity. And the average velocity is just the velocity between 2 points in general. So if we have 2 points, we've got a point here, which is x2, y2. And we got a point here, which is x1, y1. And between those 2 points, we can find the average velocity. And it is simply just the slope of this line, right? So remember that slope, of course, is rise over run. And so all we have to do is calculate that rise over run to get the slope of this average velocity. Average velocity is a very common question in a graph, and all you have to do is go from one point to another. The instantaneous velocity is a little bit more tricky in terms of just what exactly is it. Obviously this velocity is just the velocity at a particular instant. So a velocity at one time. So we know that when an object is accelerating, its velocity is continuously changing. And so we want to then be able to figure out what its velocity is at one time. We often refer to this as the final velocity in a question, but it doesn't necessarily have to be, but that's just often what we refer to it. So this instantaneous velocity is the velocity of what we call a tangent line. So a tangent line is just a line that touches the curve at one point only. So there's only one point where it touches. And so when we look at this, we say, well, how can we get the slope of a tangent line if we only have one point? Well, what we would do is we would approximate this slope just by choosing usually two other points on the tangent line. So we'd pick maybe 2 points on that tangent line. And again, we'd have an x1, y1, and we'd have an x2, y2. And we could then calculate the slope of that tangent. Okay, here's an example of how we use tangent and secant lines to calculate velocities. So the first one's asking us to calculate average velocity between 2 times. So again, that tells us that we're going to be thinking about the slope between those 2 points. And so I'm just going to locate those 2 points. I notice that my scale is going up by 0.5s for every 2 division. So that means that this division right there is 0.25 seconds. And so I'm just going to go up to the point where it is, and I'm going to identify what that point is. So that point looks like to me 0.25 seconds in the X, obviously, and I'm going to say that's about 11 seconds in the Y. In terms of significant digits, I just assume that that's 2 sig digs on that side, and so I'm going to then treat that as 1 point. The other point, it says at 5 seconds, I'm going to go all the way to there. And again, what I want is to identify the point here. So this is 5 seconds and a distance or a position, sorry, of 50 meters. So 5 seconds, 50 meters, that's my point. So the thing that we're trying to find, of course, is the slope of a line. And so what we're trying to figure out is then what is the slope of the line that joins those 2 points. And so that slope then is trying to find the slope of that line right there. So that's the secant line. So to calculate the secant line, I'm just going to use the slope. So point A here, then the slope formula, rise over run, or y2 minus y1, x2 minus x1. And so to calculate the slope, I know that I'm calculating the average velocity. And so I would then take y1, which I will say is 50 meters, and I'll subtract from that, 11 meters. Made an error in the units there. And then I'm going to divide that by the 5 seconds and the 0.25 seconds. So when I subtract this, I will get 50 meters minus 11 gives us 39. So we have 39 meters over 4.75 seconds. And then I would just divide this to calculate the average velocity. To get the instantaneous velocity at 1 second, what I would do is I would try to approximate the slope at that particular point. So at 1 second, there is a point right there. The tangent line then will be my best approximation of the slope at this point. Now, of course, this is just a guess, and so I'm going to guess that the slope looks something like this. Oops, that's not a great one. Let's undo that. I'm just going to freehand it instead of trying the straight line. So it looks kind of like that as a slope line through that one point. So that's my best approximation. And now to calculate the slope of this line, all I would do is pick 2 points. And so I would pick a point, say down here. It looks like it maybe goes through that 0 point right there. So I'll pick that point. And I'll pick also a point over here. And so I'm going to guess that it looks like about right here is a decent point there. So I've got to come up with the coordinates of those 2 points. So this point right here, it looks like this is 1.75. That's 2. So I'm going to approximate then somewhere between 1.75 and 2. It almost looks like it's halfway. And so I'm going to guess then that it is approximately 1.86, give or take. And again, it is just approximation. So that's the time. And the distance at that point is 32 meters. And then I've got another point over here that I'm going to calculate the points for that. So this is definitely 0 seconds, and it looks like it's about 12 meters there. So I just have to calculate the slope of this line doing the same kind of approximation. And so I get slope, again, y2 minus y1. And I'm going to calculate the change in these values here. So the change in y is going from 32 and 12. That's a 20 meter change. And then going from 1.8 seconds to 0 seconds is a 1.86 second value. And so in this case, we're calculating the instantaneous velocity, or we're using really an average velocity to approximate the instantaneous velocity. And so all I have to do then is just to throw that onto the Calcomatic and get to the answer for that. So if I take 20 meters, divide by 1.86 seconds, I'm getting a value of 10.75. So I'm going to say that's 11 meters per second. It's a positive value, and so we would then give this a direction as north. And then back over to the other average velocity, if I take 39 and divide by 4.75 seconds, then I also get a value over here of 8.2 meters per second. Again, it's also positive, and so that tells me that this direction is north.